I just need to make sure that the audio is working here, but otherwise, today what we were going to do is we were going to show one more reduction, one more mapping reductions following that 5-step process. Then I already called it, and we won't have class on Friday. But on Wednesday, we can show another reduction. I could dedicate it to homework questions. Whatever whatever you guys suggest, I could look into something that I haven't covered before, or some advanced topic if you want to. Let me know what you want to see. But otherwise, just making sure that it works here. Good. All right. So I wanted to show one more reduction from to what's a problem called vertex cover. So first of all, we have to define what a vertex cover is. Basically, it's a subset of vertices. Is a subset of vertices. So I'm going to label it as V prime, which is a subset of the vertex set here, such that covers all edges. Right? Now, what does that mean? It means that if I've got a vertex V, for all edges, right, it looks like this. Here's an edge. Then either it's covered by this vertex U, or it's covered by this vertex V over here, or it is a possible that they're both covered, or that this edge is covered by both of them, U and V over here. Right? And by covering, again, we just mean that this edge right here is covered by this vertex over here, or that this edge is covered by this vertex, or again that it's covered by both. Definitionally, or if that's a word, all you're saying is that V prime is a vertex cover, if and only if, for all edges E, and I'll label it as U comma V, in the edge set of the graph, that we have that U is in V or V is in V. That one of those endpoints is in your vertex cover. Here's an example. These are two separate graphs here. The first graph is covered by 3 vertices, the ones that are colored here in red. You can verify that all of the edges here, this edge, this edge, this edge, this edge, all of these edges are covered by at least one of the red vertices. Likewise, over here, all of the edges are covered by at least one of the red vertices over here. Yeah?
Why do you need the one, for the one on the left, why do you need the rightmost one red?
You don't. And that leads to a concept of a minimum vertex cover. That's the optimization problem. So here, all of the edges are still covered by at least one of the red vertices, but it's strictly smaller. Over here, we've got 2. Over here, we originally had 3. You can always have a trivial vertex cover by simply taking all of the vertices. And then by definition, all of the edges are covered. Okay? Likewise, over here, we had 4, but in the minimum vertex cover, right, then we can have 3 here. Right? These 3 vertices will cover, yes, this edge right here is covered by 2 vertices, but that's okay. This edge is covered by 1, this edge is covered by 1, this edge is covered by both, right, by 2 of those, but it's still a cover. Now, finding the minimum vertex cover turns out to be NP complete. So, what we need is a definition. So, fact, and we will actually prove this. The minimum vertex cover problem, that is, finding a vertex cover VC of minimum cardinality, or minimal cardinality, because there don't necessarily have to be just one. There could be many. You just need to find one of minimal cardinality. Is NP complete. Okay? Now, as we've observed, it is going to be much easier to talk about the decision versions of these things. And so here's the decision version. There we go. where, you know, the answer is yes or no. Does it have a vertex cover of size n? Well, that's a trivial yes, right? Because if you take every vertex, then you automatically cover every edge. So what we end up doing is we end up encoding, oops, that's ugly. We end up encoding the graph G along with a K, right? And this is going to be an encoding such that G has a vertex cover of cardinality K. Right? And again, what are the bounds on K here? It runs from 1 up to n. At the low end here, let's make some observations. At the low end here, if you had a vertex cover of size 1, what does that tell you? You could, one example would be, of course, a complete graph, right? You take, well, not a complete graph, but kind of like a spiral graph, something like this, where it's like spoking out, right? And now you only need to take this 1 in the middle right here, and you've covered all the vertices, right? So you could get down to 1. There are examples where you have that. Over here, on the other end, if you simply take all the vertices, then, you know, that, by definition, that's going to cover it. It could lie somewhere in between there. Did you have a question or another observation? Okay.
Well, if there are no edges.
Oh, if there are no edges, then, oh, okay, well, that's another good one. Yeah. If there are no edges, then, of course, I guess you could get down to 0 technically here. That would be the minimum. Okay. So we're going to go through our 5-step process here. 1, we are going to show, first of all, the vertex cover problem. The decision version is in NP. And the way that we do that is by developing an algorithm, a non-deterministic algorithm, that makes a polynomial number of non-deterministic guesses, or a guess of size polynomial, and then verifies it. So again, here's my input. A graph G equals V comma E. And because I've made the decision version here, K is also part of my input. Okay, is an integer. We're mathy. Let's say K is an integer with, I'll still keep it 1 through n here. You can take care of the 0 if you want to here. It doesn't matter. But my output will be, again, there's no output here. We accept if and only if G has a vertex cover of size K. So step 1 here, right? I'll go ahead and box this up here so it's distinct from the other one, right? We guess a subset V prime of the vertex set of size K. And again, this is going to be order K, which is order n because of our bound on n up here. And it's going to be non-deterministic. Why? Because of this guessing phase right here. It ends up being non-deterministic because you are guessing. Okay? 2, we verify. We verify by simply checking that every edge is covered by at least one vertex in that vertex set. So for each edge, E equals U comma V in the edge set of the graph, if U is not in the V prime here, and V is not in V prime here, then this is exactly the negation of the definition that I just gave you. The definition is over here, remember? That U is in V, oh, sorry. I think I screwed up on the definition. There we go. It only has to be an or. Right? I think I said or, but I wrote a conjunction instead. Sorry. Right? U is in V or V is in V. It can. That's the picture over here. This one or both is perfectly fine. Okay? But when you take the negation of this, what is it? Not, and then this becomes a conjunction, which is exactly my criteria here. If that's the case, then this is not a vertex cover, and I reject. Right? Otherwise, if I don't end up rejecting on any of those edges, I accept. Now remember, the magic of non-determinism. This entire machine, this entire algorithm here, will accept or reject based on whether or not there's at least one accepting path. Again, it's magic. Okay? That's enough to show that it's an NP. And by the way, this entire part, this is deterministic. And it is certainly order n squared, right? At most. Why n squared? Because of this for loop here running over all the edges. Okay? 2. Choose or identify an NP-complete problem to reduce from. Because if you're reducing from a known NP-complete problem, right? And in this case, I'm going to choose clique, because that's what we did last week. I'm going to reduce clique to this problem here, vertex cover. Basically, again, in more precise words here, I'm taking this clique problem and showing that it is no harder under polynomial time mapping reductions than vertex cover. Since this is NP complete, I'll annotate this. This is NP complete. By making this reduction, we're saying that this is eventually going to be NP complete, right? By transitivity. Remember that we actually had this long, not long, but this moderately sized chain of things. We took SAT and we said, without proof, that it can be reduced to 3CNF form. We took 3CNF form and reduced it to this problem, the clique problem. Now we're taking the clique problem and reducing it further to this vertex cover problem. And that chain, and by transitivity, we've shown that all of these things are going to be NP complete. They're the hardest of the hard problems as far as P and NP go. Okay? So, 3, create a map. Right? In other words, what I'm going to do is I want to take a G and I want to transform it into some other graph. I have no idea what it is yet, right? Because I haven't identified it, with the following properties. G has a clique of size, say, k, if and only if this transformed graph, G prime, has a vertex cover of size, whatever, k prime. I'll just go k prime here, right? Give it a different name. When I show you the actual transformation, when I show you the actual mapping reduction here, then these things will be identified. What is G prime and what is K prime here? Okay? But this is the property that we want. If solutions are preserved over here as far as the clique goes, and if when you run it through this mapping reduction, that it has a vertex cover if and only if this, then why is this good? Because what if you wanted to solve the clique problem? You've got an instance of clique. I don't know how to solve that. But suppose that I do know how to solve the vertex cover problem. So here's my solution for the clique problem. Simply apply your transformation, apply the solution for the vertex cover problem, and because solutions are preserved, that gives you a yes or no answer to the original problem. All right? Okay? So here's the actual reduction. What we're going to do is, given G and K, and remember I'm going to group those two things together, I am going to map that to a different graph, but very similar, G overline. What is that, by the way? G bar. That's the complement graph, right? and n minus k. There's my mapping. Now, before we prove that this mapping is right, let's understand what it is, okay? G is a graph. And here's the property. I'm going to translate that property from last time. This is what we're going to try to prove in the next part. G has a clique of size k if and only if. In other words, it goes both ways. G complement has a vertex cover of size n minus k. Oops. N minus k. Remember what n is here? That's the number of vertices. All right? That's a universal. We always just use n as the number of vertices, m, as in math, as the number of edges. Okay? So to understand this, let's go ahead and look at an example. Okay? Do I have one already, or am I going to have to reproduce it? Darn it. Oh well, that's all right. Bear with me. I'll grab this one. All right. So here's G. I'll say that I've got A, B. Actually, I don't even need to label these. Who cares? A. So there's one, there's one, there's 1, 2, 3, 4, 5, 6, and 7. And suppose the topology looks like this in the original graph. There we go. So now identify for me. I wrote it here specifically so that you could easily identify what the clique of size. I'll just tell you what it is right now. Clique of size 4. Where is that clique of size 4? Let's get a nicer color here, and I'll highlight it. Oh, it's not gonna. Okay, well, right there. There you go. All right, that's a clique of size k equals 4. Okay. Now, let's look at the complement graph. The complement graph, by definition, is the same vertex set with a complement of the edges. So the same vertex set will be the same vertices that I wrote before. 1, 2, 3, 4, 5, 6, 7. Right? But the complement is going to be flipping the edges. If there was an edge before, for example, this edge right here, then that means that it's not going to be in this graph over here. If there was not an edge, say this one and this one, then that means that there will be an edge in the complement graph. So let's go ahead and draw these things out here. This one goes to this one, and those other two over there. Right? What about this vertex right here? It was connected to these two immediately, so it will not be connected to these two over here. It was also connected to this one, so it won't be connected to that at all. But it will be connected to, sorry, it was connected 1, 2, 3, 4. So the only things that will be connected to in the complement graph are this one and this one. So I'll write that as this and this. It's symmetric, so the same thing with the one down here. There we go. What about these two right here? This one is connected to this, this, and this. So therefore, it needs to be connected to this and the original, but I already took care of that one, right? I already took care of that right here. So what else do I need to put in? This one and this one. And I think I took care of them all, right? 1, 2, 3, 4, and then 5. I think I'm missing one. What am I missing? So this one right here is connected to these two, so it need to be connected 1, 2, 3, 4. No, I got them all. I'm confident that I got them all. Right. Okay. So tell me about a vertex cover over in this complement graph. I need a vertex cover of size Over here, I told you that I was going to map k to n minus k. So in this case, n was 7 minus k. In the original graph, that was 4. So 3. There should be a vertex cover here of size 3. What is it? Far left and the two far rights. Right? You can verify visually that this is covered every single edge. What is the relationship between these two? Everything that was not in the clique over here, this, and this, ends up being in the vertex cover of the complement graph. Right? That's a cool property. So now that we understand the mapping, we need to prove that it's correct. One picture is not a proof. Right? You kind of get the idea, right? You kind of get the idea that the solutions are preserved back and forth. And visually you can, oh yeah, that works for that particular example, but that's not a proof. A full proof has you actually going through and proving that if and only if statement. We want to show that, and we have plenty of time here, G has a clique of size k if and only if G overline bar complement, right, has a vertex cover of size n minus k. Is this working? Okay, I guess so. So how do you prove this kind of statement, an if and only if statement? X, or P if and only if Q. That sounds like a contrapositive to me, and we will use that, and it's going to be really cool when we do. Right? But otherwise, if you've got P if and only if Q, you need to show one way, and you need to show the other way. So let me show the forward way first. Right? In other words, let C be a clique in G of size k. Now, like with all proofs, if you want to prove that P implies Q, which is what I'm doing here, you of course assume P. Why? Well, what if it's the case that P is not true? P implies Q here. What if this is false? Is there anything to prove? Nope. Why? Because of basic logic. That it's already true. It's not vacuously true. From a false premise, you can conclude whatever you want, right? If it's not raining right now, for those of you on YouTube, but if it's raining, which is false, then unicorns exist. If it's raining, unicorns do not exist. Both of those statements are true, right? Even though they have contradictory conclusions. So you covered stuff like this in 235, right? All right, good. All right. So all I need to do is show, well, for this part, is show from this premise that I've got this clique. Now I need to observe everything that's not in it in the complement graph. Okay. So consider on edge E equals U comma V in E complement. We need to show it is covered by some vertex. In the complement graph. Okay? So let me just go ahead and start with a series of implications here. E equals U comma V is an edge in the complement graph. We need to show that it's covered by either U or V in some manner. Right? So this implies, and this is in fact an if and only if statement, U comma V is not an edge in E. Do you see what I did there? I just simply took the negation here and I moved it over to here. Okay? Because if it's an edge in one graph, taking the complement of that graph again means that it's not going to be an edge. That's the definition of complement graph. Okay? This means that either U is not in my clique or V is not in my clique or both. Now why? Think about it in terms of visualizing here. U, V. This is not an edge. This is, well, here, I'll go through this piecewise here. This is an edge in the complement graph. Change it into the original graph, and so it's not an edge. Can those both of can both of those vertices be in my clique? Remember, what's a clique? Something where everything is connected. These two are not connected. Therefore, it cannot be in my clique. So either it could be that one of them is in the clique, but that means that the other one cannot be. It could be that neither one of them is in my clique. Right? That's why I've got the or there. I've got that either U is not in my clique, or V is not in my clique, or both. Okay? Now, what I can do is I can say that U is in the set of all vertices, set minus C, or, this is or, V is in V set minus C. There we go. All right? Do you see that? This is just the set of all vertices, and then take out your clique. Then either U must be in that, or V must be in that.
Oh, so the second V is an or V.
No, this is, okay, here. I'll go ahead and change this to or. Or, there we go. Right? And then these are all V's. Unfortunately, handwritten stuff, you do have to be careful. We have so many things that look like V's. That's why you run out of symbols eventually. That's why they use Greek, right? Okay. So this implies that UV in G complement is covered by V minus C. Right, this set over here. Now again, you can look at that from the perspective of an example, or you can look at it from the perspective of a generalized example here. Here's G. And here's my clique of size K. Everything outside this clique is V minus C. Now think about the mapping of V complement. There we go. I'll keep the same clique, but then this is my, ends up being my vertex cover. This is the vertex cover. Now consider an edge over here in the original, right? This will not be an edge over here, okay? Therefore, it's got to be, I think I lost my train of thought there.
Oh.
Say what? Go ahead, yeah.
If the clique means that all of those things are like completely connected to each other, then that means there's no connections between the vertexes inside that clique, so that means none of the vertexes in that clique are required to be.
Right. Okay. So, so look at it. Maybe you're saying what I'm about to say, but let's go ahead and consider a couple of cases here. All right. So if it straddles these two sets, right, then necessarily over here, they could be connected. It just doesn't matter, right? But one of them will be connected. So here's UV.
The optimal one would probably be. Oh, yeah, that's true.
So V is going to be covered by that edge, or V covers that edge. Yeah, Maybe this visualization's not that great.
It could technically be U, but the number of the minimal one wouldn't change.
Right. The size of here is C is K, and then the size here of this thing, V minus C, is going to be N minus K. Right? What's the way to look at this? Other than this part right here. I mean, this makes way more sense to me than the visualization, at least right now. Anyway, that's one way. Right. Okay? What I want to do is show the other way. So let me go ahead and cut and paste this statement here. This statement right here. Come on. Copy. And paste. There we go. Now I want to show the other direction. Right. So and here's my statement that I want. Let C, VC, V, C, X, W. Let's go with W. X, Y, Z, W. Be a vertex cover in G complement of size N minus K. Again, what I'm doing is I'm starting on the right-hand side here, and I'm going to show that that means that G has a clique of size K. Okay? So all I'm going to do here is, now here's where the contrapositive that you mentioned comes in. All I'm going to do is state the definition of a vertex cover. So for all U comma V in the vertex set, U comma V is an edge in the complement graph, implies that U is in C or, sorry, I use W, or V is in W. Okay? Now, take the contrapositive of this. The contrapositive does not affect the universal quantifier. And in the complement graph, the vertex set is the same, so that doesn't change either. Again, this is P implies Q. What is the contrapositive of a P implies Q? Not Q, you switch them around, implies not P. So let's go ahead and write that, and I'm going to take the conclusion and put it over here as my premise, but I'm going to negate it. So what is the negation of each one of those? U is not in W. What happens to the disjunction? Becomes a conjunction. V is not in W. Implies. Now I'm going to take the premise and I'm going to put it over here as the conclusion, but I'm going to negate it. And by negating it, all I'm going to do is take the overbar on this edge set and get rid of it. So this implies that U comma V is in the edge set of the original graph. There we go. So now read that out loud to me. For all vertices, and here W is equal to V set minus C. Right? For all pairs U and V, if U is not in the set here and V is not in the set, it means that they are connected. Well, if they're connected, what does that mean? You can form, for all such pairs that apply to this premise right here, in other words, for all U comma V in the vertex set, U comma V in V set minus C, or no, I don't want this. All right. Sorry.
V stand for the vertex set or the set of
Say that again. If V,
yeah, does V stand for the vertex?
that's the vertex set, which is the same on both graphs, right? So if it's not in this in this set and it's not, and the other one is not in this set, then that means that they're connected. Therefore, everything outside of W, which is equal to V set minus C, is connected. Right. Therefore, what? Everything outside of V set minus C, everything outside of V set minus C is a clique. How big is V set minus C? Well, the size of the vertex set is equal to n. And then we're taking out a vertex set minus this. If this is equal to n minus k, right, then if I take what do I want to say? N minus k, right? So this is going to be n minus k, the size of everything outside V set minus C is this, which is equal to k, which is what I was trying to prove, that there's a clique, everything is connected, and how big is it? Of size k. Right?
So is V minus C of size k, a clique of size k?
W is a vertex cover of size k. Therefore, or sorry, no, of size n minus k. You're right. W is a vertex cover of size n minus k. Therefore, in the original, if you just take the complement of that, then you get n minus k, which gives you k. That's the math right there. Again, it is so much easier to look at this visually for an example to get the idea. Right? Now, when you go to do your own reductions, oh, by the way, step 5. This reduction is a P reduction. Why? If I'm mapping G K to G complement n minus k, then how do you do that? Suppose that it is an adjacency matrix. How do you compute the complement graph on that? Flip the zeros, ones, right? This is going to end up being order n squared if it's a matrix of n by n matrix. Mapping k to n minus k, that's order 1, right? And you're done. Right? So it's not that big of a deal. Same vertex set, by the way. So, mapping over the data for the vertices is going to be order n, or you just copy it, order 1, whatever, right? And so this mapping reduction is a polynomial time deterministic reduction. Right? Now, when you go to do your own, mapping reductions, going through this 5-step process, generally, I wouldn't give you something that was a logic problem to a graph problem, like 3CNF to the clique, right? That means that you're encoding basically the logic of some problem into a graph gadget or vice versa. Instead, look for what I've given you is graphs to graphs. Right? Let's go back all the way over here. Right? A graph problem is very, very comparable to a graph problem. Where are we? There we go. Nope. Where's my reduction? Oh, here, this is it. All right. I'm giving you a graph problem, and that relates to another graph problem that's also hard. For example, in your handout or in your homework, you have to do a clique to an independent set, or maybe it's an independent set to clique. I forget which one. Right? The same exact trick here, slightly modified, will work, of taking a complement graph. Sometimes you have to add entire graph gadgets. For example, I think that another question asks you with a strong hint to show that, what is it? Hamiltonian path and Hamiltonian cycle are reducible to each other, or one to the other. And the hint there was simply just add a vertex and connect it to all the other vertices. Now, what properties are preserved? If there's a Hamiltonian path in one, well, by adding this one over here, you've also created a Hamiltonian cycle, right? Using that last vertex over here. Those are the basic ideas that make things comparable. Like, look for a reduction from one graph problem to another graph problem because they're going to be intimately related. If you've got a logic problem to another logic problem, SAT to 3CNF, look for a reduction among those two things. If you've got a problem based on sets, like the knapsack problem, you'll probably want to look for a reduction to another problem based on sets. Right? Yeah.
So when you say like add a vertex to turn a Hamiltonian path into a Hamiltonian cycle, would you just be checking to see if that extra vertex exists?
Well, you created it, so you don't need to check. You created it. You know it exists.
Oh.
Here's a
So
graph
it's
G.
But I thought it was a check to see if a graph was a Hamiltonian path or not.
Ham path. All right, suppose that it does.
Okay.
All right. Suppose this is the path right here. All right. Now I'm going to create a new vertex over here. Right? Now, oh, okay, well, what if I just connected it to the two endpoints right there? Right? Then that's definitely a Hamiltonian cycle. How did I know that those are the two endpoints, though? I would have had to solve the original problem. Right? You don't know that. You don't know what those two endpoints are. So, suppose that it has some Hamiltonian path here. And you connect this to everything. Right? Well, if there's a Hamiltonian path, it could have been this one and this one. Right? And then there's a path or whatever. Right? It could have been this one and this one instead. Right? And there's a path that went through all of them. You got them both by connecting it to all. Right? Now, suppose there's not no Hamiltonian path. Right? Is there any possible way that you could have induced a cycle by doing this? Probably not. Why? Suppose that there was a cycle that was induced by this. A and B. Suppose that there is a Hamiltonian cycle from A to over to B, and then to U, and then to A. Well, guess what? That's a Hamiltonian path contradicting the original statement. Right? I think I've given you the entire answer at this point, so it'll be your responsibility to restate it in your own words and write it up with a more formally than I just showed you. That was just the hand wavy part.
I was thinking like, through that problem, like, but if we add a vertex, we're no longer checking to see if the one we're currently checking is a Hamiltonian path.
No, you're not. You are transforming G into G prime. Right?
Oh, so if we
You're not solving anything. You are simply taking one problem and changing it into another problem. Right?
Okay.
And this is Ham path. This is Ham cycle. Right? Now, suppose in the future somebody came up with, I don't know, Gomer, let's say. Gomer says, I don't know how to solve Hamiltonian path, but I do know how to solve Hamiltonian cycle. Right? That means that he can solve Hamiltonian path. How? Just by taking the graph, running it through this transformation, applying Gomer's so-called algorithm here on G prime, and if accepts, then G has a Ham path. If rejects, then no Ham path. Right?
Sorry.
So suppose that Gomer stands up and says, I do have a deterministic polynomial time algorithm for Hamiltonian cycle. Well, now because this is NP complete, you've shown that P is equal to NP. Right?
Well,
And Gomer's probably wrong. Right?
but how do people disprove that something is like not actually like
That's a much bigger question of showing lower bounds. So once again, we've got this NP complete. We've got P over here, right? And again, we can use Wednesday to answer some basic questions here, but again, suppose that I don't know, there's this problem here, P. I don't want to use P. I'll call it Q. All right. Q there. Suppose that I find that there exists a polytime algo for Q. That's a breakthrough, right? Now, suppose that I want to solve the Hamiltonian path problem. Because Q is NP complete, I know that the Hamiltonian path problem, Ham path, reduces to it. Right? Now apply this algorithm A here, or transform all of PQR, R, transform R to Q, and then apply A to solve R. And you've solved the Hamiltonian path problem. What you've done to this landscape, this complexity landscape, you've collapsed it.
Right.
You've shown that P is equal to NP. Right. And there is no NP complete problems. It's all NP. Right? Yep. So the question that you asked was, how do you separate these? How do you show that P is not equal to NP? That's the $1 million question. If you had an answer to that, then you'd have $1 million. Literally, you'd have $1 million.
That'd be nice.
There's the Clay Mathematics Institute has issued a $1 million prize for it. But there are lots of barriers. There are lots of roadblocks. You've got that people have come up with over the last 40 years. Well, to show that there's a separation, you have to overcome this relativization barrier. You also have to overcome this other barrier. There are at least 3 that I know of. Off the top of my head, no, I could not quote them, but there are these 3 barriers that you would have to show. Basically, each one of those is kind of metamathematics showing that any proof that separates these two is going to have to be a completely new proof from any other proof techniques that we know today. That each one of those hurdles or barriers was a proof that this proof technique will not work for showing this. Right? It was a proof about proofs. Yeah. Yeah.
Is there $1 million prize for proving that it can't be proven?
I think that technically the wording is no, but I'm sure that you'd have. I mean, they got $1 million left over. The guy that was it the Poincare conjecture that was solved? The Russian mathematician didn't want the money, so it was left on the table. So they got some money left over to pay. Either way.
I just want my name on this.
He barely even wanted the fame. I don't even think he submitted it to a journal. He just published it and self-published and said, "Here's the proof."
He's just like, I'm just gonna sit on this for the next 40 years. It's like when I read about like the calculus, like before Isaac Newton did his whole thing, oddly enough during a pandemic, or he like this monk that was found like hundreds of years before Isaac Newton came up with calculus on a napkin
Is that Leibniz or?
or something like that.
I don't know.
His name, but I'm just like saying, he really did just like.
Oh yeah, their stories are.
He just decided to come up with something
Well, I'll go ahead and see you next time here, but there's